So let's get started. We'll work on the second part. One of the question I think I did not do in the class, which was then the sheet. Let me start with that. See, the body initially at initial velocity is 0. So let's see, you can imagine I have not marked here. Let's say it is somewhere here. It is initially, it is here. And it starts slipping on the inclined plane, forming an angle alpha. So most cases, even if figure is not given, you should be able to draw a figure. The coefficient of friction mu is varying with distance s from here. As the distance increasing, what is happening? Coefficient of friction is increasing. So as the this mu is function of distance from the starting point. So as the friction keeps increasing, it means what will happen? The frictional force also will keep on increasing, whereas the downward force, which is mg sin theta, remains constant. So if this friction force keeps increasing, of course, what will happen? Initially, it will have downward acceleration. That's why it started slipping. And as the friction keeps increasing, when friction force becomes equal, its downward acceleration becomes 0. After that, further it will keep moving. And when the friction force becomes greater than mg sin theta, it will start slowing down and finally it comes to rest. So what is given in this question? We don't have to apply laws of motion. See, if we have to do laws of motion, what would happen? It will have start with a downward acceleration, which will slow down. Downward acceleration will decrease. It will become 0. Then it will have retardation. So that is laws of motion, but we can solve this question much faster and lot more easier with use of work energy theorem. So what we need to do here, we need to find what distance the body stops. That makes it a little easier. So if it stops here, means here also velocity is 0, here also velocity is 0. So it starts at rest and finally it comes to rest. So it means if it is rest and rest state, change in kinetic energy is 0. So then we apply work energy theorem, work done by all forces equal to change in kinetic energy. So work done by all forces between initial position and final position has to be equal to 0. So then we come to, when it comes, let's say this stops in distance s or L. Work done by friction plus work done by gravity over the distance s has to be 0. That's what it said. Only two forces are doing work. Friction force, the normal reaction is not doing work. Gravity is doing work and friction force is doing work. What is work done by gravity? Gravity is a constant force which is easy to calculate. So gravity is acting downwards. And we try to understand what is the direction of displacement. Displacement is happening in this direction. So we take the vertical component of displacement into gravity. That's work done by gravity. So vertical component of displacement is, if the distance it comes to stop is s, vertical component h becomes equal to s sine alpha. The work done by gravity is easy. If I call this distance as s, it is mgs sine alpha. That's the work done by gravity. Now, when we come to frictional force is changing with s. And when it is s changing with s, what we need to do? We need to take work done over a small random length s. What is work done over a small length level? The friction, see, displacement is happening in this direction and friction force is acting in the opposite direction. So what we need to do? We need to write for a distance, some random distance s from here. Coefficient of friction is mu s, and friction force at any point, we are talking about kinetic friction, will be equal to coefficient of friction into mg cos theta normal reaction. But this is function of x, so we write, so what is the work done over a small distance ds? Friction force into ds minus sign, because angle is 180. So minus sign into coefficient of friction, which is b into s, into mg cos alpha, and displacement is ds. That's work done over a small length ds. We add it up from 0 to L. This becomes work done by friction force start from between initial point and final point, if L is the stopping distance. This S is the direction. If L is the stopping distance, this becomes my work done. So if we calculate work done, so it's very easy to arrive at this value. It becomes ds square by 2. We simplify, we get our answer. So what is the distance L we obtain from here? This question, which was then the sheet, I didn't finish. Let's come to some other questions now. See, in this arrangement shown in the figure, block A is released from rest. This is block A. Two blocks are connected here. And spring is in the natural length. So it is released from rest when the spring is in natural length. Okay. The question is, for the block B of mass m to leave contact with the ground, what has to be the minimum mass of A. So if mass is small, this block will remain on ground. But for particular value of capital M here, this mass, the block B, will leave contact with the ground. So before we solve this question, we have to understand one more part here. What is the other part we need to understand? If the mass M is released from rest with spring is natural length, what will be the maximum extension of the spring? Why we have an interest in calculating maximum extension? Because when we know the maximum extension, the force exerted by the spring on block B will depend on its extension. And this extension will depend on maximum displacement of A. And that's why we need to first calculate what is the maximum displacement of A if it is released from rest. So what we'll do now, first we'll calculate what will the maximum displacement of A. How would we calculate that part? So let's see, this is the initial state when the string was natural length. And this is the state, this is initial state. Here, this state corresponds to maximum displacement of A. When the displacement of A is maximum, its velocity will be 0. So initial condition, just released, final condition, when extension is maximum. So here also velocity is 0, and here also velocity is 0. So these are the two states. So most questions in the conservation of mechanical energy, important point is to understand which are the two states to which I need to apply conservation of mechanical energy. So left one indicates initial state, right one indicates final state. Question is, if it has moved down, it has a displacement h here, and we are still assuming the block B has not moved. That's what we need to calculate. So it has come down by distance h. So this part of the length string, the length has increased by h. Where from this increase in length of h has come? Because string on other side cannot extend. So what has it extend? Whatever displacement block A has had is only because of extension of spring. So it has downward displacement of h. It means spring extension also should be equal to h. That's a condition. And since this has come to a rest, what is rest means here? A momentary rest. It has come to a momentary rest. So if this one is in the state of momentary rest, the rate of change of length of the string also is 0. At this particular instance, rate of change of length of the string is 0. Length is not changing. If length is string is not changing, string is not changing. So in that case, the string force has to be equal to spring force. I am mixing up spring and string. Let me be more careful, but I hope all of you understand when is spring and what is string. So let me repeat this point again here. So what are you saying here? What does h mean? H is the maximum displacement of A. If the displacement is maximum, it means at this particular time it has come to a momentary rest. So when this has come to momentary rest, it has displacement h. So length of the string has increased. If the length of the string has increased on the right hand side, it can only be because of extension of spring, because string length here cannot change. Okay, so this extra length, so extension of the spring also is h. So let's solve based on this now. These are the two states. Let's apply conservation of mechanical energy to the whole system here. On the left hand side, what is the whole system? Two masses and the spring. Let's apply conservation of mechanical energy. And what is a dot? What is the line I have drawn here? Because in this case, whenever gravitational potential energy is involved, we need to take a reference point, a reference level. So typically it's best to take the reference level at the lowest point so that all potential energy becomes positive. So I have taken the reference level as the final position of block A. This is a reference level. So what are the initial position? Initial position block A was higher by distance h, hence its potential energy is mgh. At this stage, its kinetic energy was 0. It just started release from rest. And potential energy of spring also is 0 because spring is unextended. So this only energy here this system has with this reference here is mgh. Now coming to this side, this has still not left the ground. So kinetic energy of this block has become 0. This has 0 energy. Potential energy of this block is 0 because that's the reference level. Only thing left is potential energy of the spring. Potential energy of the spring is equal to 1 by 2k h square, because that's the extension of the spring. So from here, what we find the value of H, which is the maximum displacement of the block, is equal to 2 mg by K from this equation. So what we notice is this important point, I think we had discussed last year as well. So whenever we release an object from rest which is connected to spring, its maximum displacement is twice the weight by K. Why it is twice the weight by K? Because if I release it, you know what kind of motion this will have? If I just leave it like this, suddenly I release it, it will come here. Will it stay at this point? It will not stay at this point. Okay, at this point, if you look at this also, what is the spring force acting? The spring force acting is 2 mg, which is acting in the upward direction. Now at lowest point, it has upward acceleration. So it will have what kind of motion? It will have SHM motion. So these 2 points here, state A and this final state, both the position velocity is 0. So these 2 states indicate extreme position of SHM of object A. So these are extreme position, and at both the extreme position, acceleration is maximum. At upper extreme position, acceleration is G downwards, and lowermost position, acceleration is G upwards. So this I'm just basically covering. Similar thing will repeat in case of SHM motion. This object A will undergo SHM motion. So what we understood, as it goes down, as it keeps having downward displacement, the spring keeps getting extended. The spring force also will keep increasing, and spring force is increasing. The tension in the string also will keep on increasing. Upward force on block B also will keep on increasing. Okay, so if the block B has to leave the ground, the maximum spring force has to be greater than weight of the block B. That's the condition. So maximum force on the spring is twice mg. That's what we really understand, and twice the weight. Block B will leave the ground if maximum spring force becomes greater than weight of the block B. So that's my equation. So what equation I substitute? This is a condition here, which tells you block B will leave ground if capital M is greater than m by 2. It means the weight of this block, mass of this block, if it's greater than half this mass, this block will leave ground at some stage. And if it is just twice, it means when it is the lowest, when it is a death stage, if capital M is exactly equal to m by 2, what will happen? When it has the lowest most position, this force here will be equal to mg. The normal reaction will just become 0, but block B will not leave the ground if it is just equal to m by 2. So is this understood? And you can visualize. So suppose what is this one here? What we see here, 10 kg block is pulled along a frictionless surface in form of an arc of a circle of radius 10 meter. So this is center of the circle O, and radius R is given as 10 meter. And this is arc of a circle. It is placed, this is something what we see, it is lying in a vertical plane. Okay, and there's a pulley here. It's a very small pulley. We apply a force of 200 Newton, constant force. Force remains constant here. So that's what is given here. Initially, the block was at this position. As we keep applying this force, mass of the block is, where's the mass given here? 10 kg mass. So 10 kg mass, this force is greater than its weight. So naturally what will happen when you apply this force, this block will move along the surface and it reaches up to point Q, very close to the pulley. So what we need to calculate when it reaches this point Q, and Q here, if we connect here, this whole segment makes an angle of 60 degree, initial position being vertical. So when it reaches Q here, what would its velocity be? That's what we need to calculate. And when it reaches here, what is the work done by gravity? This is 2 things we need to calculate here. Let's see how we go about. See, as soon as we look at Q as a system, now here Q only is moving under motion. So can I apply conservation of mechanical energy only to system of this block? If I take this 10 kg block as a system, can I apply conservation of mechanical energy here, Vignesh?
No, sir, because there's a non-conservative force.
Non-conservative force is acting, is doing work. So every time when we choose my system, so we need to identify the forces which are doing work on the block. So one more force which is doing work on the block is tension. And tension is having, so here displacement is like this and tension is like this. It is not perpendicular, it is doing work. So here, moment you notice here, if I take this as a system, there's a non-conservative force as well. So what equation I'm going to use? Work done by non-conservative force. Here work is done by conservative force as well as non-conservative force. So I'll write this, I'll use this equation, and it's not difficult to figure out. Is work done by non-conservative force is equal to change in potential energy plus change in kinetic energy. And when I change, this is my initial state and this is my final. So change means final minus initial. So let's look at what is work done by non-conservative force. Non-conservative force, as far as the block is concerned, is tension T. But tension T is same as force F. So this T is nothing but F. So whatever you see, what another important point one need to understand here, this string. See string, what does string and pulley do? What does pulley does? Pulley only changes the direction of force. Whatever force you applied here, had the pulley not been there, it would have been straight. So pulley changes the direction. And what does string do in this case? String, external agent, we are applying force here. Suppose you are standing here, you are applying a force of 200 Newton. So when you pull this pulley, when there's a displacement also, work is being done at this point. So what is the role of the string? Whatever work is done at one end of the string, same work is performed by the string at the other end. Because string does not retain energy. String is not like a spring which can store energy. So work done by this end of the string is same as work done by external agent on the other end of the string, which makes it a little simpler. So this is a small point, an important point to understand here. So what is work done by string force on the block is equal to force work done here. What is the work done? Work done, this particular force is moving in the straight path. So all I need to know, as the block moves from P to Q, what displacement this force of 200 Newton will suffer. And it's very easy to figure out. Displacement here will be equal to length PQ. Initially, the length of the string here was PQ. Final stage, the length of string has become 0. It means here the length of the string has become shorter by length PQ. So here also the length of string should move by distance PQ. So what is displacement here? Work done by 200 Newton force is equal to 200 Newton into displacement, which is nothing but equal to PQ. And since this angle is 60, this is radius, it is equilateral triangle. So displacement PQ is equal to R itself. So what is work done? 200 joules is the work done. Work done by tension force on the block. So I equated work done here is equal to work done by tension force on the block. So we calculated this. Now we are left with other two. What is increase in potential energy? Thus, as far as gravity is concerned, we are only concerned with vertical height and is going up. So potential energy has increased by how much? Mg into delta H. What is the height gained here? This angle is 60. Very easily you can calculate. The height will be R by 2, which is 5 meters. So delta H, it has gained a height of 5 meters. I think this equilateral triangle, all of you can easily figure it out. So increase in potential energy equal to mass into G into H 5 meter, 500 joules. So I have rest of the things. So kinetic energy is initial 0. Now I can calculate final kinetic energy. So if I use this equation, increase in kinetic energy is equal to 1500 joules. Since initial kinetic energy is 0, this itself is equal to KE final kinetic energy, which is equal to 1 by 2 mv square. I get the velocity at point Q, which comes to something like this. So let's move to the next question. It's like this. In this question also, release from rest. And there are two blocks A and B, both bars M and N masses are equal, connected by two pulley and string system. And what we need to find here, see this case, we can easily find it out. As soon as we release this system here, the question is, will it remain in equilibrium or one of the block will move down, another will go up? And which is perhaps easy to figure out. Why it is easy to figure out? If I assume this tension to be T here, this also will be T, and hence this tension will become 2T. So what we notice here, the upward force, both have same downward force mg, but upward force on A is greater. Hence A will have tendency to move up and B will go down. So even otherwise, if it is not given the question also, we could have figured out the B will move down, A will move up. And see, virtual work is easy to understand in case of when all the block and strings are vertical. So this tension is T and this is 2T. So if this has velocity V, this will have V by 2. And we can do it another way also. So this is what I understand. This will go down, other will go up. Let's go and solve this question. So first thing what we need to understand, what we need to find here, what is the velocity of block A when block B has fallen distance L? So this has gone down. So when it has fallen distance L, we need to find out what is the velocity of A. And so let's see how do we proceed here. See, first thing what you need to figure out, the displacement on speed of A will be half of B. How do we do it? I think if you want to follow only one method whenever string is involved, follow this method. What is the method here? Let's say the velocity of B is V. Because whatever relationship we have velocity, same thing will be there in case of acceleration. So if this point has velocity V, this side velocity is 0, because this is fixed here. Pulley will have a velocity V by 2. So with this V by 2, it means this part of the string has velocity V by 2. So what is the velocity other one has? This pulley is at rest. It means both this average of these two velocities should be 0. If average of 2 by 0 means if one is going down the velocity of V by 2, other has to move up with the velocity of V by 2. So with the very simple use of velocity of pulley being average of the velocity of two sides, I can calculate if this was V, this is V by 2. That's the first thing we need to figure out. So what is the first thing we have concluded? This is the point. Displacement and speed of A is half of B. So if B, this is displacement as well as speed. So if I call this as V, this will be V by 2. That's the first part we have concluded based on our constraint motion. Now let's look at the next part here. Let's visualize this figure, what has happened here. See, this has moved by distance. This I have drawn. So this is initial state. So whenever we have to apply conservation of mechanical energy, we need to be clear with two states of motion. Because what are two states of motion? Initial state and final state based on what we need to find. In final state, what is mentioned? It has moved by a distance L. So this is something, clearly you see the block B has moved by distance L and block B has a velocity V. What has happened to A here? A has moved up by distance L by 2 because the velocity is half and displacement also is half. And if this is velocity V, at this instance, it has velocity V by 2. So at this particular instance, this velocity is V and this velocity is V by 2. And in this case also, work is being done. See, strings are all work. We can conserve mechanical energy here. There's no friction and there's no loss of energy. So let's apply conservation of mechanical energy between initial state and final state. Okay, so that's the one way you can do. Or in this case, wherever spring is not involved, we can also simply write when mechanical energy is conserved. We can also think whatever kinetic energy is come. Initially, there was no kinetic energy. So gain is kinetic energy is equal to is coming at the loss of potential energy. So whenever such question, I can write conservation of mechanical energy. But one question I thought I'll do in slightly different way. What is the kinetic energy gained here is equal to loss of potential energy. So I'll calculate what is when does the loss takes place. Potential energy loss is when it moves downwards and it is gained when it is moved upwards. So when we calculate loss of potential energy, who is losing potential? What is the loss of net loss of potential energy? See, block B has moved down. Block B has lost potential energy and A has moved up, it has gained potential energy. So what is the net loss? Net loss is, how do we calculate net loss? So change in potential energy, this one is negative because it's come down. It has come down distance L. So this is minus MGL for this is for block B. And for A, it has moved by distance L by 2. So there's a plus. So what is net change in potential energy? Negative sign indicates there's a loss of potential energy. How much is that? MgL by 2. So I hope this part is clear. Change in that's a change in potential energy, which is equal to loss. So what is delta K? What is change in kinetic energy? Change in kinetic energy, final kinetic energy minus initial. Initial, there was no kinetic energy. What is final kinetic energy? Kinetic energy of block B plus kinetic energy of block A. That's what he written. This is kinetic energy of block B. This is kinetic energy of block A. Velocity is V by 2. That's the kinetic energy. So either I could have written delta P plus delta K is equal to 0, or you can also think of Ke gained is equal to loss of potential energy. So now I write this equation, delta P plus delta K is equal to 0, which basically equates this term to mgl by 2. So in this equation, I can easily find the value of B, but question asks not the value of B. B is the velocity of B. What we need to find here, velocity of A. Velocity of A is V by 2. So V by 2 is this term by V by 2. So that's the velocity of block A. So I am assuming that rest of you also, if anybody has not understood, you can ask now. It's there on the screen. Again, all the figures are there. I can re-explain if something is not understood. Please raise your hand and clarify. Okay, so I hope all are clear. Let's look at the next question. And this question was a bit tricky one. This is past mains question. And this question, you notice here, there's something new in this question. And let's pay attention. And if we don't notice that part, what I'm going to explain here, it would have become a lot more difficult to solve the question. And reason I'm taking this question, pay attention, something similar may happen again also. Let's read this question. Overall, it is not too difficult a question, but there was something which is a little tricky. So let's see what is given the question. I have converted information given the question in form of a figure. A body of mass 1 kg. So this is mass which is 1 kg, which falls from a height of 100 meter on a platform of mass 3 kg. So this is a platform here. This platform itself has a mass of 3 kg. So this platform is 3 kg means spring is already compressed. This platform is lying on the spring and spring constant K is given. What is important to notice, K value is very large here. So if you have to calculate what was the initial compression of the spring, X naught, it will be equal to mg by K. Mg is 30 divided by K. If I have to write, K is 1.25 into 10 to power 6. So it is very, very small. It is of the order of not even centimeter. It is order of millimeters and even less. So that's the one thing we should have noticed here. Initially, it is compressed, but compression is extremely small. Okay, and it falls from a height of 100 meter. So this is what happened first stage. And so let's read through, and it falls on 100 meter, and its body sticks to the platform. So if the collision was, it like kind of collision here. I have taken this question here in this chapter is inelastic collision, and inelastic collision is a very simple thing. So what will happen? They'll stick together, so momentum will remain conserved. So what will happen in case of whenever inelastic collision, if it comes and strikes velocity v, if velocity of 1 kg block was v just before collision, after the collision, since the mass has become 4 times, velocity will become 1/4. Velocity becomes v by 4. That's the conservation of momentum. And second thing, what we notice here, see, if the kinetic energy was k here earlier, then the mass has become 4 times, velocity becomes 1/4, kinetic energy also becomes 1/4. And that also we can easily arrive at. And we'll do it again in case of collision. So whatever kinetic energy it had just before collision, after the collision, in inelastic collision, there's a loss of energy. Energy is not conserved. And if I calculate, I could have very easily done that also. Let's see. So initially before collision, 1 into V has to become equal to, total mass becomes 4, 4 into V dash. V dash is V by 4, velocity becomes 1/4. And kinetic energy, initial kinetic energy was equal to 1 by 2 into 1 into V square. And after collision becomes 1 by 2, mass becomes 4 times 1, but velocity becomes v by 4 square. So 1 mega, it becomes equal to k by 4. And that's what we have to keep in mind. So this part is coming from collision. Let's understand now. Let's go and solve this question. So what we need to find is sticks together. We need to find the maximum compression. From this point, what is the further distance it gets compressed? So I have drawn 3 figures here. What are the 3 figures here? This is just before this mass strikes this platform. This is when they have stuck together. And third step, when it comes to maximum compression. Maximum compression means whenever we talk of maximum compression, at this stage velocity is 0. It has downward velocity become 0. So it has 3 phases. What are the 3 phases here? And let's understand this question. It's a good question. First phase is when it is falling from here to here and it has not yet struck the platform. During this phase, its mechanical energy is conserved. So whatever potential energy was there, it has lost potential energy equal to mgh. That entire potential energy has become into kinetic energy just before collision. So what is kinetic energy just before collision? The kinetic energy is equal to mgh. If we put mass is 1, g is 10, and it is 100, it is 1000 joules. So that's a kinetic energy of mass of 1 kg just before collision. Now it goes to the second phase. What is second? Second, very brief period of inelastic collision. Inelastic collision means it gets deformed. It doesn't regain its shape. There's a loss of energy. There's a loss of energy, but momentum is conserved. So we conserve momentum, so no displacement. So this is very brief period. A large impulse will act on both the blocks. A big impulse will act on 1 kg in the upward direction, and on the platform in the downward direction, and they'll stick together. They require a common velocity. Since the time interval is very small, during the period of inelastic collision, displacement is almost zero. We always consider this happens in very brief period of time, no displacement. So no compression, no displacement of 3 kg block or the spring. So what is the final kinetic energy? So this we put together. After the collision has taken place, final kinetic becomes half of the initial kinetic energy. I have given the reason, and becomes 250. So now onwards, what will happen? So this is the first period, energy was conserved. Second period, there's a loss of energy, momentum is conserved. And third phase is after the collision gets over, till it gets maximum compression. Now, from this phase to this phase, mechanical energy is again conserved. Now, we are taking system as this block and spring system. So compression of spring, it comes to momentary rest. That's a maximum compression. It is a state of momentary rest. Mechanical energy is conserved. So I'm applying conservation of mechanical energy to this part and this part. And since the gravitational potential energy is involved, I have chosen a reference level for gravitational potential energy. That this lowest level is reference level. So let me write energy here and energy here and equate. So what is the energy here at this state? It is potential energy of the mass of 4 kg. The potential energy of mass of 4 kg. So that will be equal to mg into x. Mg into the total mass into g into x height. Thus the potential energy of the gravitational potential is mgx. Kinetic energy I have written 240. And this is potential energy in the stored in the spring already. But I know, so these are terms here. Kinetic energy 250. Potential energy is stored in the spring plus potential energy of this mass here. That would be equal to sum of 3 forms of energy: kinetic energy, potential energy of the spring, plus gravitational potential energy. Kinetic energy in final state, kinetic energy will be 0. Gravitational potential energy is 0. And this will be equal to 1 by 2 kx square. See, what was important when I was talking on this question? See, when we have this term here, there are 3 terms on the left hand side. One term is kinetic energy, which is 250. And we have already seen here what would be the potential energy stored in the spring. See, if you have to understand, in potential energy stored in the spring will be equal to 1 by 2 spring force into x compression. So that will be equal to 1 by 2 into mg into compression. And what will be gravitation? So these numbers, since x is so small, I am not calculating the number. I think moment is 10 to the power 6. That's what it should come to your mind. Compared to 250, these numbers are less than 1. I can neglect this number. Then only becomes easy. Otherwise, this becomes like a quadratic equation, becomes a little cumbersome to solve. Now, if we neglect these 2 numbers, I take this entire energy equivalent to 250. So some of you can check and try and understand why I'm neglecting these numbers. So this x is extremely small. And I'm equating it to this one. I'm just ignoring the initial compression x here. I'm equating to 1 by 2 x square. Because I'm saying this initial xi was so small that final compression also, and this xi term I'm ignoring. 1 by 2 kx square, and x comes to 2 centimeter. When I write this one, it becomes easy and it's extremely quick to solve. So key point here was understanding the 3 terms involved. Out of the 3 terms, 1 term is much larger compared to other 2 terms. And it is much larger because here k value is very large. I can ignore these terms. If I do not ignore, try and solve, it takes a lot more time. And options given the exam also was 2, 4, and simple terms. So I hope this is understood. Yes, Vignesh? Let's move to next question then. So this question is potential energy of particle oscillating on axis is given. And oscillation may not necessarily mean SHM. We can check a particular type of oscillation only is SHM, which can be verified. We can do that. And we'll see in this case also whether we can check whether it's SHM or not, though SHM topic will come later. What are things given? This is how potential energy is. And total mechanical energy of particle is also given. So this is something. So see, if you want to understand this question, we can also relate to something like this, simpler way. See that how it is related, and just doing something which will helpful for SHM also. So suppose we have a spring connected, and spring is connected to mass, and spring constant is K. Okay, so when I displace this mass here, if this I take as x is equal to 0, I would have written the potential energy corresponding to displacement is equal to 1 by 2k x square. Then when I take a mean position, where is the mean position taken? At unelongated length. But I can shift my origin somewhere else also. What happens if I shift my origin to some other point? Or what if we can thus when I shift this origin, this x term also will become, if I shift towards left, it will become x minus 2. So if I take an origin 2 meters left of the unextended length, it will become potential is equal to 1 by 2k x minus 2 square. Where is the plus 20 term coming here? Can you think of reason why this plus 20 term will come? If I have a spring mass system. Huh?
So we take zero potential energy below the Earth.
Yes, we in this case, if see all cases when we write potential energy of a spring equal to 1 by 2 kx square, we are assuming two things. We are assuming x as the position when it is spring is unelongated, and second thing we are assuming the potential energy in unelongated state is 0. But we are calculating change in potential energy. If I assume potential energy of the spring in its natural length equal to 20, that for any other position, I have to add the potential energy everywhere. So this indicates something like that. So if this is the potential energy, it is not given here, but suppose, could it possibly indicate potential energy of a spring mass system? Yes, it can indicate. What are the difference here? Origin is not at the unelongated length position, and at unelongated position, potential energy is not taken to be 0. So that's a okay, it's a different thing. Let's coming back to how else we go about solving the question. So the rest of the solution is fairly simple. If this is a potential energy, how do we find the mean position? Can we think of way of finding mean position? And then we have to find maximum kinetic energy. How would you find mean position here? Tejas, can you tell me how do you find mean position here?
Yes, sir. At the mean position, potential energy of it will be 0, right, sir?
Potential energy 0 at mean position? Not right.
Not right, sorry.
Now, what is 0 at mean position? What does mean position mean? What does mean position mean? What it means, mean position means net force has to be
Net
0.
0, okay, yes.
No, the force has to be 0. So that's the point. And what is force equal to? But potential is going to given here. We need force to find mean position. But what is force is equal to? We have done that yesterday also. Force is equal to negative derivative of potential energy. And this partial derivative, let's see, so x direction, potential energy will change only because of force in the x component of force. So we find fx is equal to negative of this derivative. This derivative would have come as 2x minus 4, negative, it becomes 4 minus 2x. This is how force will vary with position of the object. What is mean position? When the net force becomes 0. Net force easily you can come out, it becomes 0 at x is equal to 2 meter. Now we have to find what is the maximum kinetic energy of the particle. How do we find? And from this equation, do we figure out will it have SHM motion or will it have some other type of oscillation? Will it have SHM motion? Yes or no? And if yes, why? Jaideep, can you tell me, will it have SHM motion? Yes or no, and why? So whenever force is proportional to negative value of displacement, it is such a motion. It will have such a motion, and which mean position at x is equal to 2. So this is force is proportional to x, linearly proportional, negative is such a equation. Mean position is 2. How do you find maximum kinetic energy? So when in this case also, only force acting, since moment we define potential energy, it indicates force is conservative. Hence, mechanical energy will remain constant. What we have to use, mechanical energy has to remain constant. Mechanical energy is sum of potential energy plus kinetic energy. So kinetic energy will be maximum where potential energy is minimum. That's the second point we need to understand. So what does mean? We have to say total energy will remain constant. So Ki become maximum where potential energy is minimum. Maximum potential energy minimum. And when is the potential energy minimum? This is square term. The minimum value of this term has to be 0 only. So minimum value of potential energy is 20 when x is equal to 2. At x is equal to 2, this is minimum potential energy. Okay. And when potential energy minimum at x is equal to 2, kinetic energy will be maximum. So when is the kinetic energy maximum? At the mean position, which happens in case of SH motion. And what is the kinetic energy? We equate total energy to potential energy plus kinetic energy corresponding to x is equal to 10. So x is equal to, x is equal to 2. So x is equal to 2, if we substitute, total energy is 36. P is equal to 20. And we get K max. What is K max equal to? 16. So that's the maximum kinetic energy. Okay. And suppose I extend this question, I also want to find out what is the maximum displacement for the mean position. The maximum displacement indicates what? Maximum displacement, whenever object has maximum displacement in case of SHM, its velocity is 0. Kinetic energy is 0. So in that case, what has to happen? If kinetic energy is 0, so whenever it oscillates in SHM motion, I hope all of you recall these basic points here. When it oscillates like this is the mean position. This is plus extreme position, negative extreme position. That's amplitude oscillation. At this point, what happens? Kinetic energy has to be 0. It reverses direction. So that's what maximum displacement from mean position will correspond to kinetic energy being 0. So entire total energy is in form of potential energy. From here, if we solve, we get, this gives you, this is equal to 16. So mod of x minus 2 is equal to 16. It gives you two position, x is equal to 6 and minus 2. So it will have such a motion between x is equal to minus 2 and 6. And if I have to plot, this is okay. So this is how the something like potential energy is. Potential energy is minimum at x is equal to 2. And it is increasing. So this is shape of potential energy curve. It is similar to spring curve. Only thing what has happened, we have added 20 everywhere, fixed amount, and we have also shifted the origin. So this is potential energy curve. And if I have to mark total energy, in this case, total energy, this quantity is 20. Total energy given in this case is 36. So if I draw a line, this is total energy 36. So it means wherever at this point, what will happen? Can this object go to this point? No, it cannot go to this point here, because in that case, total energy will exceed the energy given to this particle here. So this is a point here when total energy in form of potential energy, kinetic energy is 0. What does this point correspond to? Here, potential energy has become maximum. This is my kinetic energy. And at any other position, if I take at this particular point, what will happen? This will be the kinetic energy and this will be the potential energy. This is how it will oscillate. So if we just visualize here, so this is the point mean position, kinetic energy becomes maximum. This is how the oscillation takes place. And this is the position of, this is the shape of potential energy. We have done, I have mentioned yesterday also. This is whenever it forms a kind of a saucer kind of shape. And this object will be, this is the state of stable equilibrium. And if I draw the force here, the slope is positive and the force will be negative. Here the slope is negative, force will be positive. And force we have already seen here, force will be linear function of position. The force will vary like this on the particle. So this whole thing indicates a condition of stable equilibrium. What happened if this case, it was given a total energy of 36. What happened had we given energy of not 36, suppose we given a total energy of only 25. what would happen? So the particle is here. If it is given energy of 25 only, what would happen in that case? When it reach this point. So in this point, what will happen? Then I draw a line which is at total energy equal to 25. It will oscillate between those 2 points. So if it is here, just you can imagine. If say something, this shape also you can visualize. If there is a ball lying here, if you have more energy give, if you give less energy, it will oscillate with lesser amplitude. As energy given keeps increasing, if energy increases, it will reach a highest point. It will reach will correspond to kinetic energy being 0, total energy being equal to potential energy. So if you look at the graph, you can understand some bits which will come into such a motion. Okay, so is this understood?